I'd like to talk about big statistics, which is really the statistics of big data. So I'm going to talk about tall data and wide data, and data when there's too many things to look at, issues of selection bias when you're looking at a lot of things, representing the p-values from big data, and issues of practical significance when everything is significant if you got enough observations, but it may not be practically significant. And we'll look at survey data, genomics data, process data. We'll look at issues of robustness when there are outliers, informative missing when there's lots of holes in your data, and the importance of good hardware and software. First, let's look at tall data when there's lots of observations. So here's all the website. You can download all the flights from all major airlines from 1987 to 2008. It turns out there's a lot of flights, about 123 million. This is easy, it's just more data, the same kinds of things you do, and even if the data's big, it doesn't take that long to analyze it because computers are fast. So now let's see if the situation changes when we have wide data. There's lots and lots of variables and lots of things to look at. So here's the General Social Survey. Again, more than 20 years of data from 72 to 2012, and it's reading all these variables in. And now we see that, there's 5,562 variables. That's a lot of data to look at. So whenever you're dealing with a lot of variables, there's a lot of things to look at. And so it's a different world with wide data. Wide data means there's just a lot to look at. And sometimes you can ignore a lot of stuff and you just want to look at what changed the most, And that's very important for process change. When you're looking at genome-wide association studies, you just want to find out the genes that really matter from the different things, and a lot of the genes won't matter, and so on. So when you're doing this kind of thing, the biggest problem you're going to get, or one of the biggest, is selection bias. So you're looking at lots and lots of tests, and you've selected out the most significant of those tests, and you've sorted them. And by random chance alone, you're going to get some significant tests. And the neatest example I have is I took archery lessons a couple years ago. And they give you 50 arrows, and so I shot 50 arrows. And so I took all the arrows out of the target, and some of them didn't even hit the target. They went all over. It was my first archery lesson. But by chance alone, one of the arrows hit the middle of the target. That's the one I took a picture of and put on Instagram and told my kids about. So by random chance alone, we're going to get significant tests. And if you do that thing in statistics, with doing lots of tests and just selecting out the significant ones, then you're going to get selection bias, okay? In fact, there's a name for it. It's called p-hacking, And so when you do lots and lots of tests and so on, you get into trouble. So you need to take care of selection bias. So how do you do that? Well, it turns out there's a neat way of doing it. And this was pioneered by the people that actually had a lot of questions to look at in the beginning, back in the 90s. And genomics, for example, there's billions of base pairs and millions of SNP variations and tens of thousands of genes and so on. So the old way to do this was something called the Bonferroni correction. And you took the p-value criterion, like 0.05, whatever alpha, and you divided it by the number of tests. So if you had 1,000 tests, it was 0.05 divided by 1,000, and that was the new criterion. Okay? Well, that turns out to be a very stiff criterion. And it was hard to get any genes to look significant with the Bonferroni. So they said, well, we need to do something else. We need a different approach. And so a new concept was developed back in the mid-90s. Benjamin E. Hochberg had the first great paper on it. It was called false discovery rate. So rather than controlling for any errors, any type 1 errors of declaring something's non-zero when it is, you want to just control the rate, okay? The rate of discoveries that are false, the expected value for that. So that's called the false discovery rate. And it turns out there's a very easy way to do it, and this is really revolutionary statistical genetics for all these association studies. So you think about what a p-value looks like when there is no effect. So here's an example where I took all these process variables, against just lot-to-lot variation. And so it's a stable process. There's no variation in there. So what's the distribution of the p-values that comes out in this case? And it turns out to be the uniform distribution. And you can see these red p-values plotted as they go up from the lowest to the highest, and they pretty much follow a uniform distribution. So that's when there's nothing there. It's a uniform distribution, and about 5% of them land under the 0.05 significance criterion, if that's your alpha, just by chance alone. It's exactly what you'd expect. Now, if you took the Bonferroni correction, you would take 0.05 divided by number of tests, 388 in this case, and you'd make that the criterion. That's shown on the very left. It's a very tiny thing. What Benjamini-Hochberg says is you take the very least significant p-value and you compare that to 0.05, or your alpha. And then you take the next most and you compare that to 0.05 minus a little bit. And you basically build a ramp, and that's that red line there, that goes from 0.05 for the highest p-values down to the Bonferroni limit of 0.05 divided by the number of tests at the other side. And if your p-value gets under that red ramp, then it's significant, controlling for false discovery rate at 0.05. And it also meant that you could adjust your p-values, take a whole population of p-values and adjust them in such a way that you get these blue dots, and the blue dots will go under the blue line at 0.05. At the same time, the red dots go under the red line, which is 0.05 adjusted for false discovery rate. So we can get false discovery rate p-values. Those are the blue lines there. And notice none of them get under the blue line. None of them are significant because there's no effect here. So what does it look like when there is an effect and you get all these p-values? Well, in this case, about 35% of my tests are not significant, and they have pretty much a uniform distribution. It's all the values above the red and blue lines. And then all the significant ones are well below that line, and so about 65% of these tests are significant. There was a big enough change when I changed my process that it moved the needle on these mean process variables. Now, the other thing to notice is, hey, all the things that I don't care about because they didn't change, they're all nicely separated in the top part of the plot. But all the values that I really care about are near the bottom, near zero. And so I can't separate them. I can't find out whether one's just merely significant or very, very significant. So we need to change the scale on this thing. And so I call this the reverse Anna Karenina principle for visual p-values. So you've heard of Anna Karenina. That's the Tolstoy novel. It starts with happy families are all alike. Every unhappy family is unhappy in its own way. And the statistical corollary is that null hypothesis, if you satisfy the null hypothesis, it's all the same. But there are many ways to not satisfy the null hypothesis. That's the statistical version. And so the visual version is that, we want the significant values to separate nicely because they're interesting, and we want all the non-significant ones to cluster together. And so the way you do that is by taking the logarithm. And so next slide shows the logarithm, and now we see the p-values getting extremely small, and all the non-significant ones are crowded at the top. So let's look at some other issues. When we have a lot of data, like millions of data, we know that the standard error, the mean, is so tiny that everything's going to be significant, even if it's a really teeny tiny effect. And so when you do significance tests, everything looks significant if you got enough data. So you don't really care about tiny differences. You usually care about differences that are big, okay? And so to be sensitive to those big differences, it's really better that you take your test in a different place. Instead of testing that a difference is 0, which is on the left, you test that a difference in absolute value is greater than some value you care about. And the other way is sometimes you want to find out what you don't need to care about. That's because it hasn't changed anything. You want to go run the test the other way so that you're ensuring that it's near 0. Well, you can run the test in a different way, and it's called an equivalence test. And this is the test that drug companies do when they want to prove something is equivalent to something else in an FDA submission. They show equivalence tests. And basically, they take some value that basically equivalent, some practical difference, and they prove that the actual difference is less than the practical difference in one way and in the other way, and that's the two one-sided t-tests. So you can combine the practical test and the equivalence test when you're looking through data and basically get a three-way answer, okay? So you get the plain p-value you usually don't care about because everything's different if you got a big enough sample. Then you get the practical difference p-value, and that's proving that there is a difference, and those are highlighted red in here. And then there's the equivalent ones where you're sure that the difference is less than a certain absolute amount. And then if it isn't one of those two, then it's inconclusive, and you don't know whether it's equivalent or different. Now, a few other things with big data you need to take care of, and one is outliers. You get this all the time in economic data, I'm sure, and it happens in industrial data and so on. Your data is often well behaved for most of the values, but a few values are way out. You know, in semiconductors, there's a voltage spike because some insulator is not working, and so it goes way up. And you need to take care of those outliers so that you remain sensitive to the mean shifts in the other variables. And so you use robust estimates. And so you build these robust either Huber estimates or Cauchy estimates, and there's others, but those are the ones we tend to implement and jump. And you look at the false discovery rate for the Huber estimates, and then you see here that, there's a lot of significance on the Huber scale, and we saw some things that we didn't see on the original scale because they were masked by outliers. And so if I look at the details of that, I can see that one variable, and I can see, there's some big outliers here on the new side. All the old ones seem kind of clean, but the new ones are spread out and got some serious outliers going there. And that's kind of masked the difference. If I did ordinary test of means, I'd get a p-value of 0.18, not significant. But if I do the robust, my p-value is less than 0.001, highly significant. And the reason why is the standard error of the means are different. Those outliers inflate the standard errors of the means, so it makes it difficult to detect significance. What's another factor that you want to adjust for? That's holes in your data. If you have a lot of holes in your data, you better think pretty seriously about it. So here's some economic data. This is mortgage delinquency. So this is whether a loan went bad on a mortgage, and there's lots of missing values in it, like debt-to-income ratio, missing, delinquency, missing, a lot of times. So if you're going to fit that, what do you think? Do you think if someone doesn't tell you their income and debt, that the loan is better, or that we should throw that out of the regression? If you do, you're going to bias the result. And here's an example where we do logistic regression on whether the loan went bad. And if I do the traditional thing, which just skips the rows that have missing regressors in them, I get an R-square of 23, and I've thrown away essentially almost half, 3,300 out of 5,900. I don't trust that. Those results are biased by all those missing values. And the missing values here are going to be informative because if you hide your income and debt and so on, you're more likely to probably be in default. There's a way to actually take those missing values and convert them into regressors by having indicators of missing and then offsets from those indicators that you code your regular variables to. Then you can bring in all your data. That's called informative missing. And so with informative missing turned on, I got all my data in now. I've raised my R-square from 23 to 45.7. So I've doubled my amount of fit, almost doubled the number of observations, and look what comes up most significant. Debt-to-income ratio is missing. Not reporting your debt-to-income ratio is highly predictive of your mortgage default. So whenever you have lots of holes in your data, you have to take care of that problem, and one way of doing it is called informative missing. So that is my talk, and thank you very much.